So before we finish up, I want to talk about two more things. One is the meaning of what are called unit vectors, I, j, and k. I don't know if we've named them before, but they're called the unit vectors. And the other is vector multiplication. So I, j, and k. Remember, we defined I, j, and k as meaning just in the direction of the plus x-axis, plus y-axis, plus z-axis. But they actually have a further meaning than that. They indeed do mean that for us, but they have a further meaning. They are called unit vectors. And what that means is that they are actually vectors with length 1, with length unity. So I is a vector of length 1, of magnitude 1, no units, of magnitude 1 pointing in the x direction. Etc., etc. So j is a vector of magnitude 1 pointing in the y direction. Whoops, there's my x's looking like y's. And k is a unit vector of magnitude 1 pointing in the z direction. So they are vectors. I, j, and k are vectors. They're called unit vectors. And you use that vector to multiply it by a scalar in order to get a vector of length that's equal to that scalar that's in the direction of interest, right? So if I take my unit vector I, which is length 1 in the x direction, and I multiply it by 3, then it's going to be 3 times 1, or a vector of length 3 in the x direction, right? 3i means a vector of length 3 in the x direction. So one of the things that I just did without even just assuming you understood is we just did vector multiplication. I multiplied a vector that has a magnitude of 1 by a scalar 3. And when you multiply a vector by a scalar, what do you get? You just multiply the magnitude. You just multiply the magnitude. Sorry, you just multiply the magnitude by the scalar. So let me give another. So first of all, let's just make sure we understand the unit vectors are actually, they mean in the direction of for us, but they also are vectors that just have magnitude 1. So let's go ahead and just do an example of scalar multiplication of a vector. So I just rewrote what we just said, right? If you have a vector I and a scalar 3, and we want to multiply the scalar times a vector, 3 times I is just 3i. That, I think, is understood. And we can do the same with any vector. Let's say I have a displacement vector, an arbitrary displacement vector. I just made it up. And it's 10 meters in the I direction and 14 meters in the j direction. So it looks something like this. Let's put it on a graph. 10 meters in the x direction, 14 meters in the negative y direction. So my displacement vector looks something like that. And let's say I multiply that by 3, right? Let's multiply it by the scalar 3. Multiply it by the scalar 3 times d is equal to, right? It's going to be a vector, which is, I didn't leave myself enough room, but we have 3, I'll draw it on a new page. If my vector was like that, d, then 3d should look like that, right? It's 3 times d, but it's also the same as multiplying the magnitude of each vector component by 3. So it would be 30 meters I minus 42 meters j. So multiplying by a scalar is obvious. But there's other kinds of multiplication. You can actually multiply a vector times a vector. So you can actually multiply a vector times a vector. We will use vector multiplication. We're not going to use it in this chapter. We won't use it until we get to the energy chapter. But let me just point out that vector multiplication, in other words, a vector times a vector, multiplication, if we have vector v1 and vector, well, sorry, let me stop a second. So let me take that back and say, let's say I have 2 arbitrary vectors. I don't care what they are, velocity, acceleration, force, whatever. 2 arbitrary vectors, A and B. They have x and y components like this. When we do vector multiplication, there are actually 2 kinds of vector multiplication. There are dot products and cross products. and they are used for different things. And we're not going to talk about what they're used for now, but if you haven't done this math before, don't worry about it now. We'll teach it to you when you need it. But just keeping in mind that vector multiplication is not as trivial as scalar multiplication. When you're multiplying a vector times a vector, there's what's called a dot product, A dot B, and there's a cross product, A cross B. Those give you different results. The dot product is also called the scalar product, and because it ends up giving you a scalar as a result, and the cross product is the vector product because it gives you a vector as a result. But anyway, we're not going to do those kinds of multiplications right now. You read about them in the book, and we will learn them when we need them. Okay, so that's all I got for you with vectors. We're going to move on now to two-dimensional kinematics, which is the interesting part that we are going to use vectors for. You may ask, well, wait, you did that really quickly. Can we do more examples? But more examples is not going to help you. What's going to help you is practicing what you've already learned. I've done a couple, 2, 3, 4 examples of vector addition using components, right? Whenever you want to add two vectors, you've got to put each vector, or add more than two vectors, you got to take each vector, put it on a coordinate system, take its components. If you're adding the vectors, add all the x components, and add all the y components so that you have one resultant vector where you have an x component and a y component. And then you can put that back on a coordinate axis and turn it back into a magnitude and direction by just drawing a right triangle. So vectors is all about just drawing right triangles, taking the components, adding them together, putting components back together in a right triangle. So there you go. Don't forget that subtracting a vector, a minus b, is the same as adding two vectors, a plus a negative b. And remember that a negative of a vector is just the vector turned around, right? So if b is this, then negative b is that. Whoops, negative b is that. Whoops, that was a bad drawing. So we know how to add vectors using components. We know how to subtract, because subtraction is just addition of vectors that are negatives. And we know how to multiply vectors, right? 3 times a is just 3a, etc., etc. We don't need to know cross products or dot products yet. Okay, so that summarizes it. That's it. Call it a day. Have a good night. See you tomorrow.